I wanted to go over related rates with you. Right here I have an outline of the procedures that can help you to go through a related rates problem one step at a time. It's really an extension of implicit differentiation. If you remember, when our x's and y's were intermingled, I mentioned that you could really take the derivative with respect to anything. And with related rates, you're taking the derivative with respect to time. Now, let's read these real quickly. First, you identify the rates in the problem. Of course, you have to notice that you have a related rates problem first, but that's usually pretty apparent when you see that there'll be two or more rates in the statement of the problem. You identify those rates, the ones that you're given and the ones that you need to find. Sorry about that. From your vast mathematical history, you try to find an equation that ties the two subjects of the rates together. Most of the time, these will be from geometry. Take the derivative of that formula using implicit differentiation, but instead of taking the derivative with respect to x, take it with respect to time. So you'll have dv dt, dh dt, dr dt. Everything will be with respect to time. Plug in the known rates. Now, here's something that I've said in the past few years since the Harry Potter movies came out. Sometimes students plug in too much. Don't be tempted to plug in the specific values when they say, how fast is it going when something is true? Don't use that value until the end. I usually say, put that in the snitch. It only is used at the close of the problem. Solve for the unknown rate, and then you're at the end of the problem, so then use that value that you've put off using. Now, I made a program to give the simplest introductory type problems for related rates, and you can see it right here. These are typical scenarios. You see water going out of a conical tank, or you see a pile of a cone being created, or you see a ladder sliding down a wall. Now, this ladder one can show you oops, I lost the ladder. The ladder one can show you, let's start again, can show you that at first, though the ladder is being pulled away at a steady rate, it's sliding down the wall at various rates. So though the rates are related, they are not proportional. Here are ripples in a pond, or a balloon deflating. So let's look at the sort of questions. Now, these are, as I said, introductory questions, and I have posted this on the school website so that you can practice. Let's see if I can get this program down within the window. I'm really having a great time here. Maybe there. Let's look at some of these. These are, here's a problem. Let's look at this one. This one's kind of easier. I did a volume problem on another media player, and you might want to look at that one after you see this one, if we get any progress here. A pebble is dropped into a calm pond, causing rings in the form of concentric circles. The radius of the outer ripple is increasing at a constant rate of 3 feet per second. How fast is the rate of the total area of disturbed water changing when the radius is 2 feet? Now look, you've got two rates. You've got this 3 feet per second, and then they want to know how fast is the rate of the total area. So there are two rates involved in this problem. dr dt, and there's dr dt, which is known as 3 feet per second. And then they ask you to find how fast is the rate of the total area of disturbed water. So they're asking us to find dA dt. So here's a known rate, and here's an unknown rate. So what we want to do here is, and let's see, how fast is the rate of the area changing when the radius is 2 feet? So like I was saying, take the radius is equal to 2 feet, and do not use it at the beginning of the problem. Save this till the very end. I'm putting it here in the snitch. So I'm going to try to come down here and get some space to work on in the, I lost it again, in the smartboard. Probably I'll lose this again. Let me see if I can manage to bring the smartboard down here. Okay, we have this ripple effect, and the pond is the water is being disturbed in the pond, and we have a radius of the disturbed area, and we have an area. So out of our vast mathematical knowledge, do we know how the radius and the area are related? Well, the area of a circle is pi r squared. I hope you all remember that. Now we need to take the derivative, not having any luck this evening, take the derivative of this a equals pi r squared with respect to time. Now the derivative of area with respect to time is dA dt. The derivative of the other side, since we have an r squared here, it's going to require us to use some chain rule stuff going on. So we're getting pi is a constant, so we'll put pi, and the derivative of r squared is 2r dr dt, because we're taking derivative with respect to time, and a rate is not time. So now we have two rates in our equation after taking the derivative implicitly with respect to time. Now we want to solve for this dA dt, so luckily for us it's already solved for that. You plug in the known rate, which was this 3 feet per second, so we see that the area is changing at a rate of 2 pi r times the known rate, which is 3, or 6 pi r. So dA dt is changing at a rate of 6 pi r. So now plug in that r is 2, and we get, this is changing at a rate of 12 pi, and let's see, this is dA dt, so it would be feet squared per second. Wire is in the way of my feet squared per second. And that's a poorly demonstrated related rates problem. Once again, let's look back at the procedure that you should go through when you do a related rates problem. First, identify the rates in the problem, the ones that you're given and the ones you need to find. Secondly, we try to find an equation that ties those subjects together. We just saw that it was area and radius. It might be height and volume. You might even be given 2 rates and be asked to find a third. Find something that ties all that together. Take the derivative of that formula, and this is the weird thing, using implicit differentiation with respect to time. There probably won't be a time variable in that equation, but the derivative of A with respect to time, area, is dA dt. The derivative of the radius with respect to time is dr dt. The derivative of h with respect to time is dh dt. And use your chain rule problems, and you can take the derivative of these quantities with respect to time. Plug in the known rates. Don't use a specific value usually stated in the final portion of the problem, and solve for the unknown rate. After you get the unknown rate, it can be used to find the rate at any specific time. That's when you plug in the specific value. I hope that this is enough to help you if you get stuck.